Thanks for inviting me to speak at this really interesting workshop. And also, thanks to the organizers for putting together such an interesting array of talks. So I should start probably by saying that my area of expertise falls strictly in this and beyond part of the title. And so hopefully I will be able to clearly explain the relationship of some of the positive structures that we've been hearing about to some of the things that I work on more closely. Okay, so the starting point is the fact, which we've already heard about, especially earlier today, that this remarkable fact that actually positive geometries the positive geometries that underlie scattering amplitudes actually applies to more than just very specific theories. So originally it was understood, more specifically in the context of things like n=4 super Yang-Mills, but now we understand that these positive geometries actually arise in just run-of-the-mill effective field theories. And so, yeah, as I've just mentioned, these generic effective field theories enjoy a positive geometry. We already heard very nicely how that works, and this is called the EF dihedron. And what the positive geometry is describing is really, it's describing the space of consistent effective field theory couplings. And so one of the observations that we've already heard a little bit about is that actually the known examples of effective field theories, in fact, cluster near the boundaries. And so this suggests that we really do need to, if we want to, describe more precisely physically reasonable theories, then we need to augment our set of consistency conditions beyond those which are already maybe defining what we're calling the EF dihedron. And so one example of a physically reasonable condition in theories of gravities that's not encoded in the EF dihedron, obviously, is the idea that at high energy and fixed angle, we expect scattering amplitude to be exponentially soft in energy. So on a very sort of different side, in theories of gravity, the holographic principle offers sort of an entirely different perspective on the underlying structure of observables. And so what this more specifically means is that observables in theories of gravity can be identified with observables in non-gravitational theories in fewer dimensions. Or in other words, it's simply equally valid to interpret these observables as arising from non-gravitational theories in fewer dimensions. And the most famous and well-understood example we have of this is the ADS-CFT correspondence. And here, one of the nice aspects of this correspondence is that our command of conformal field theories enables us to, in principle, learn something about quantum gravity in asymptotically ADS spacetimes. Now, if we try and move beyond this particular instance, well, in asymptotically flat spacetimes, scattering amplitudes constitute a natural set of well-defined observables. And moreover, so amplitudes, right, are functions of asymptotic data that's specified at the past and future boundaries. And of course, they're commonly interpreted as describing the result of time evolution through the bulk from the past boundary to the future boundary. But you nevertheless might imagine answering the scattering problem without ever referring to time evolution through the interior. And so, for example, one way to do this would be to identify scattering amplitudes with other known mathematical objects. And that's sort of been one of the themes of this conference. But alternatively, or one might be able to find a holographic dual theory whose observables can be identified with scattering amplitudes in asymptotically flat spacetime. And so thus, the central question that underlies the holographic approach is there an intrinsically defined dual theory whose observables can be interpreted as scattering amplitudes in asymptotically flat spacetimes? And so the current status in answering this question is that at present, essentially the symmetries that we understand about these systems supply the strongest evidence for the existence of an intrinsically defined holographic dual theory. And so what do I mean by that? Well, in particular, so the scattering problem in theories of gauge and gravity, is constrained by infinite dimensional symmetries, which are known as asymptotic symmetries. And the symmetry constraints on scattering amplitudes that are in fact equivalent to soft theorems. And so a particularly interesting instance of this is the fact that the so-called subleading soft graviton theorem implies that the gravitational scattering problem in 4 dimensions admits a Virasoro symmetry. And so what we learn from this fact is that a necessary property of a dual theory is that it admits the conformal symmetry of a theory in 2 dimensions. And so this suggests that the holographic dual theory is a theory that lives in 2 dimensions. And so in order to further investigate this proposal, it's helpful to work in a language in which the underlying 2 dimensions are manifest. And since, as I said, this 2D conformal symmetry was the origin of the 2 dimensions, the idea is that we should explicitly organize our scattering data in 4 dimensions according to this symmetry. And what we gain from doing so is that we should be able to identify scattering amplitudes in 4 dimensions with 2D conformally covariant correlation functions. And scattering amplitudes that are recast in this way have been called celestial amplitudes. Okay, so the outline for the remainder of my talk is that I'm going to more explicitly review the definition and construction of celestial amplitudes. And so in particular, celestial amplitudes, so I've sort of already described them in one way, but another way to think about them is that they represent the scattering of particles in boost eigenstates as opposed to momentum eigenstates. And then we're going to explicitly study the 4-point massless scalar celestial amplitude. And and the sort of 2 things that I want to convey to you is first how one can canonically extract the EFT hedron, the EFT couplings from this object. So the EFT, so we're going to study some of the analytic structure of this object and see that there is a very simple way to extract the EFT couplings. And these are the quantities that are lie in the EFT hedron. And the second thing is that this soft behavior, or exponentially soft behavior at high energy and fixed angle is also reflected by a simple analyticity condition on this 4-point massless scalar celestial amplitude. And so the idea is that if we had a little bit more control of the entire analytic behavior, then we might be able to understand the way in which this condition could further impose constraints on the EFT couplings. And so most of what I will be discussing is based on this paper that appeared in December with Nima, Anna Ricariu, and Andrew Stramaja. Okay, so as I said, the first thing is to explain in more detail how one constructs these celestial amplitudes. And so as I said, the basic idea is that we wanted to organize the scattering data according to this 2D conformal symmetry. And so the first thing to ask is, so what is really the origin of the 2D conformal symmetry? And there's a very simple, this can be understood very simply, and that is that the Lorentz group of 4 dimensions, SO3, 1, is isomorphic to the global conformal group in 2 dimensions, SL2C. And so what we want to do is we want to organize the scattering data according to this SL2C symmetry. And so if we're studying a massless scattering problem, a nice way to parameterize the scattering data is in terms of these spinor helicity variables. Okay, so now if we study, so this is, we should ask how the spinor helicity variables transform into the Lorentz group. And so in particular, so this is well known, they transform by acting with an element of SL2C. And what I'd like to point out is that actually, if you look at the ratio of the 2 components in the spinor helicity variable, well, that transforms like a coordinate on the 2D plane under a global conformal transformation. And so what this suggests is that since we can use these spinor helicity variables to parameterize the massless scattering data, it suggests that we identify in the spinor helicity variables, their ratio can be transforms like the coordinate on a 2D plane under a conformal transformation. This suggests that we might be able to identify single particle states with local operators that live at these points in 2 dimensions. So to make this suggestion more precise, the nice thing to do is to explicitly parameterize the spinor helicity variables in terms of the plane. So I said the ratio should be identified with coordinates on the plane, and then I have this omega to take care of sort of the overall scale, and eta is a sign plus or minus 1, depending on whether the particle is incoming or outgoing. And so then you can work out that under a Lorentz transformation, these spinor helicity variables parameterized in this way transform like this. And so in particular, this overall scale, omega, gets shifted by this factor here. And we see this little group phase can be explicitly written in terms of the A, B, C, and D that are parameterizing our Lorentz transformation. Okay, so as I said, since we could identify the ratio of the spinor helicity variable components with coordinates on the plane, that suggests that we might be able to identify states with local operators in 2 dimensions. Now, if we're talking about a conformal field theory, there are a sort of nicer preferred set of operators are the primary operators. And this is essentially, so primary operators diagonalize 2 of the 6 generators. And so in particular, they diagonalize dilations and rotations about a point. And so, they're preferred essentially because they are organized in a nice way according to the the global conformal symmetry in that they diagonalize the maximal number of generators. And so in particular, primary operators are labeled by net conformal dimension and spin. And so these are the eigenvalues under the dilation and rotation. And they transform under a general Lorentz transformation, or under a general conformal transformation according to this rule. And H and H bar are just the left and right moving weights, which are related to the net conformal dimension and spin. And so if we compare this transformation, we should compare this transformation to the transformation of states that are parameterized by the spin helicity variables, which then we rewrote in terms of energies and points on the sphere. And so these momentum states transform in this way. Now, since this little group phase, I remind you, takes this form, we see that this transformation is actually almost this type of transformation. And so in particular, we see that the coordinates on the plane, as we already said, transform in the proper way. And at least it has the sort of right transformation if we just look at the spin degrees of freedom, the spin part. And so in particular, what that tells us is that 4D helicity plays the role of 2D spin. And so the only remaining thing is that for primary operators, there is this second label of net conformal dimension, which is diagonalized. And so it is the same under these transformations, whereas for the spinner, when the momentum states, we have this other scale omega, which transforms non-trivially under the global conformal transformations in 2D, or equivalently the Lorentz transformations. And so obviously they cannot be identified with one another, but they should be related in some way, since we've sort of, we've already taken care of all the other labels. And so in order to obtain states of definite conformal weight delta, as opposed to being parameterized by this sort of energy omega, we really want to diagonalize this transformation. And this is just because, as I said on this previous slide, the transformation of this parameter omega is just by the sum overall shift. So suppose we want to diagonalize this transformation. So the infinitesimal version of this transformation, the generator of that is something like this. And, just like the Fourier transform diagonalizes just the derivative operator, this sort of operator is diagonalized by a different type of integral transformation known as a Mellin transformation. So this thing here. And so then you can check that under this sort of a transformation, if you take a Mellin transform of it and instead label, replace your label of omega by your label of delta, now it transforms in this way under this. So this transformation becomes this under the Mellin transformation. And so that is the answer. So we can construct so-called conformal primary states by taking ordinary momentum states, parameterizing them in terms of points in 2 dimensions and an overall scale omega, and taking a Mellin transform with respect to this parameter omega. And the upshot is that these states transform under the Lorentz symmetry in 4 dimensions like primary operators under the global conformal symmetry in 2 dimensions. And so you can see this explicitly in that you take this transformation rule, you plug it in here, and you do a change of variables, and that correctly gets you the part here that is raised to the power delta. And now if you want to study scattering amplitudes between such states, then all you need to do is you need to take your ordinary momentum space scattering amplitudes, parameterize them again in terms of every state in terms of a point in 2 dimensions, a spin, and a net energy, and Mellin transform with respect to these energies. And the objects that you get are the things that are called celestial amplitudes, and they transform under Lorentz transformations like a correlation function of primary operators in a 2D conformal field. Okay, so this is just saying in equations what I just said. So by construction, this is the transformation of celestial amplitudes under the Lorentz group in 4 dimensions. And so several comments are in order. So the first thing is that because we Mellin transform with respect to the energy of each particle, these scattered particles are no longer carry a definite energy. And so in general, the notion of energy is obscured in this basis. And essentially we replace that label of energy with a label of conformal weight instead. And so in particular, as I sort of mentioned in the introduction, one of the things that we're going to be interested in is the way in which the effective field theory expansion appears in these objects. And based on this idea that the notion of energy is obscured, it's not even obvious a priori that an effective field theory expansion should be natural at all in celestial amplitudes. But as I'll explain later, actually, it's a very the effective field theory expansion appears in a very simple way in the celestial amplitudes. And the second thing to say is that while the notion of energy is not obvious, the notion of angles is actually preserved. And this was simply because the coordinates on the plane were already appeared directly in these spinor helicity momentum variables. So that is just to say that whatever angle one was talking about originally in momentum space is still directly captured by the z dependence in the celestial amplitudes. Maybe I should say, are there any questions at this moment? Okay. Okay. So now what we're going to do is, since we're interested again in how the sort of EFT expansion coefficients appear in these objects, we're going to be interested in the 2-to-2 scattering celestial amplitude because it's the one that is related to the ordinary momentum space 2-to-2 scattering amplitude for which these constraints are derived. And so the first thing we want to do is sort of start from the ground up and ask, based on the symmetries, what is the most general form of the 2-to-2 scattering, 2-to-2 celestial amplitude? And so the first thing we want to do is study the constraint, the effect of the kinematic constraints, or in other words, Poincare, on in this new language. So, by construction, we constructed the celestial amplitude to transform under the Lorentz group like a 4-point correlation function in a 2D conformal field theory. And so therefore we can just take what we already know from conformal field theory and directly apply it here. So that is to say that the z dependence of this 4-point celestial amplitude is entirely fixed by SL2C or equivalently the Lorentz group in 4 dimensions up to an undetermined function of the conformal cross ratio, which is this ratio of the 4 points. And so, in other words, there is this kinematic factor here that takes care of all the non-trivial transformation properties under SL2C. And then this conformal cross ratio is invariant under SL2C transformations. And so the 4-point function can always be written in this form. But because this object is really supposed to describe scattering in 4 dimensions, right, it is also constrained, it's constrained by the full Poincare group. So in other words, it includes the translations in 4 dimensions. And so in momentum space, momentum conservation enforces these constraints, but now we're no longer working in momentum space. And so we need to understand the constraints. The constraints are not obvious. So to understand the way they arise, there's the following argument. So the first thing is that, so in momentum space, right, the constraints from translations are fulfilled by momentum conservation. So momentum conservation, in particular, forces all 4 spatial momentum to lie in the plane. And this is just to say that, okay, the spatial momentum are 3 component vectors, 3 of them therefore specify a plane, and momentum conservation forces the 4th one to be in that plane. Now, this plane, so while we can think of these coordinates as parameterizing a 2D plane, by the stereographic projection, you can equivalently think of it as a 2-dimensional sphere. And this plane intersects that sphere on a circle. And so what it tells us is that momentum conservation forces the 4 points Zi to lie on this circle. And now if you rewrite, again, sort of undo that process and rewrite this circle in terms of these coordinates on the plane, then what one finds is that momentum conservation forces the conformal cross ratio to be real. So in other words, what we've learned is that this undetermined function of the conformal cross ratio actually has to be proportional to a delta function that forces the conformal cross ratio to be real. And so that's to say that based on these arguments, that the celestial amplitude is constrained by Poincare up to an undetermined function that depends on the real part of the conformal cross ratio, and that's possible. But if we think about it this way, actually, this is a little bit disappointing. And in the sense that we would really expect Poincare to be more constraining. And why is that? Well, let's recall the story that happens in momentum space. So if we study 2-to-2 massless scalar scattering in momentum space, well, we can do the same story. First ask about Lorentz invariance, and Lorentz symmetry tells us now that the amplitude must be a function of only the invariance we can construct. So in other words, the different Mandelstam invariants. But then if we impose translation symmetry, what we learned is that actually only 2 of those are independent. And so we typically take these to be, for example, the center of mass energy and the momentum transfer T. And so what this says is that if we did the story in momentum space, then our scattering amplitude is fixed by kinematics up to an undetermined function that only depends on 2 parameters. Whereas previously we found it depended on the real part of the cross ratio, so that being 1, and then all 4 conformal dimensions. And so the question is then, well, does something similar apply to celestial amplitudes? So to answer this question, the first thing to notice is that actually this conformal cross ratio, one can identify it with the ratio of these two mantle-stem invariants, and this is essentially because in this ratio, the overall momentum scale drops out, and so this is really telling us something about angles. And so then the question is, well, what replaces the overall energy scale in the celestial amplitude? Now, to answer this question, let's revisit this massless scalar 2 to 2 celestial amplitude and just write it. And so in particular, start with our constrained form in momentum space and take the Mellon transform. So in momentum space, again, we had this sort of the dynamical content, which is this unconstrained function of two of the Mandelstam invariants. And since the ratio of the two Mandelstam invariants could be identified with the conformal cross ratio, we parameterize them in terms of that, and then some overall energy scale, which we'll call omega. Now, again, in momentum space, translation invariance is enforced by this by momentum conservation, which appears as a four-dimensional delta function. And we argued that one of those constrains the conformal cross ratio to be real. Then the other three we can write as constraining ratios of the energies of the external particles. And finally, this was the Mellon transform, and we can rewrite this measure in terms of this overall energy scale that we introduced for the Mandelstam invariance, and then also in terms of three ratios of energies. And here I've introduced this parameter beta, which is given by the sum of the conformal dimensions up to some net shift. And so the point of writing it this way is now we can see that three of these delta functions localize these integrals. And so we can just simply perform those integrals. And what we find is that the 2 to 2 massless scattering, or the 2 to 2 scattering, the 2 to 2 celestial amplitude can be written in this form. So basically here we have, again, the part that we could have used our knowledge of conformal field theory to find. This was part of the remnant of translation invariance. And this remaining part is where all the dynamics happens. And so remarkably, it's simply related to the object in momentum space in that one parameterizes S and T in terms of an overall energy and their ratio, which is the conformal cross ratio, and then you Mellon transform with respect to that overall energy. And so again, it is only a function of two variables, this parameter beta, which was the sum of the conformal dimensions, and the conformal cross ratio Z. And so what we've learned is that the center mass energy is traded for the sum of the conformal dimensions, and that this dynamical content in the celestial amplitude is related to the dynamical content of the momentum space amplitude just by a single Mellon transform. Okay, so at this point, we've learned what we've learned how much, we've sort of figured out how much we can get from just the kinematic constraints or Poincare symmetry on celestial amplitudes. And our goal now is to understand the further constraints imposed on this object by unitarity and causality in 4 dimensions. And so one way to get at this is that in momentum space, as we already heard in more detail in the previous talk, that causality and unitarity in fact imply positivity conditions on the coefficients of the EFT in an EFT expansion. And so in particular, if you take the momentum space scattering amplitude and Taylor expand in S and T, then these coefficients are forced to obey an infinite number of positivity conditions. And so we already heard a lot of this in the previous talk, so I will, and this is also not my area of expertise, so I'll be brief. But let me just sort of briefly review this story. So what is the origin of this positivity? Well, the idea is that causality and unitarity allow us to have some control or assume some control over the analytic property of amplitudes. And ultimately, that enables us to write the 2-to-2 scattering amplitude in this or as a dispersion relation. So these are the subtracted terms, and basically up to subtractions, it's telling us that we can understand the scattering amplitude in terms of its both discontinuity or singularities along the positive along the real s-axis. So the poles being associated to so the residues of poles, and then discontinuities for particle production. And then moreover, Lorentz invariance and unitarity tells us that these the residues and discontinuities are positively expandable on Geigenbauer polynomials. So that's just to say that you can expand them on the Geigenbauer polynomials, and these coefficients are positive. So putting those two together, you can put sort of write this general form of the dispersion relations. And the goal then is to determine the positivity constraints on these coefficients, A, K, Q, that follow from the positive structure associated with these propagators and the positive structure associated with the Geigenbauer polynomials. And so, as was explained just in the last talk, you can understand sort of the positivity arising from the propagators by taking sort of this simple example. And if you expand this F as a Taylor expansion in S, then, well, you can just do this exercise, and these are the coefficients. But then geometrically, what you learn is that this vector F, which is given by just all the coefficients of this Taylor expansion, lies in the convex hull of the continuous half moment curve 1x squared, and so on, where x is 1 over m squared. So similarly, to understand the positivity associated with the Geigenbauer expansion, you can consider sort of this toy example. And then similarly, you consider what happens when you expand in both S and T and find some expression for the coefficients. And and in particular, and so this is the expression from the coefficients that you get simply by Taylor expanding this thing. And so then here, geometrically, what you learn is that now if you work at fixed K, you have a K plus 1 dimensional vector. So it's fixed K and all possible powers then of Q. And that vector lies in the convex hull of the Geigenbauer derivative vectors, which are formed by taking these Geigenbauer polynomials, taking derivatives up to a factor, sort of just a factorial factor, and then evaluating them at x equals 1. And so what you learn then is that, okay, the space of consistent effective field theory coefficients and consistent with unitarity, causality, and Lorentz invariance is given by a polytope that's characterized as the convex hull of some collection of vectors. So here being either the moment curves or the Geigenbauer derivative vectors. And of course, it's preferable instead to specify the polytope by the inequalities that are associated to its facets. And as we heard in much more detail in the previous talk, if we're interested in the positivity in sort of the inequalities associated with the facets for the first case, so the one that came from the propagator positivity, then we should form this Hankel matrix and demand that the minors are positive, and also look at the shifted Hankel matrix. And so this is mathematically solving the problem. What is a space specified by the convex hull of the continuous half moment curve? And likewise, for the Geigenbauer positivity, the sort of important point is that these derivative actors actually form a cyclic polytope for which we know what the facet structure is. Okay, so this was just a sort of a brief review of this idea that unitarity, causality, and Lorentz invariance imply that these effective field theory expansion coefficients must satisfy an infinite number of positivity constraints. And this forms what is known as the iptahedron. And so now we're going to sort of put these two ideas together. And so in the celestial amplitude story, I remind you that all the non-trivial dynamics, so in other words, everything that is not fixed by Poincare symmetry, is now captured by this single Mellin transform of the momentum space amplitude, where we've parameterized, we've let Mandelstam invariant S equal to omega squared and T equal to minus C omega squared. And beta is the sum of the conformal dimensions. And so if we want to understand, so one of the things we want to understand is in particular how these coefficients, which must satisfy an infinite number of positivity constraints, appear in this object. And the answer is that to figure this out, all we need to do is we need to consider only the contribution from the lower range of integration of this object. And this is because sort of this expansion comes from expanding about S and T equals 0. So in particular, if we now take this expansion and let S equal to omega squared and T equal to minus C omega squared, so that's this here, and we simply look at what happens from the lower range of expansion, well, then we find that these coefficients, AKQ, so the coefficients are now the residues of simple poles in this parameter beta at negative even integer, at negative even integers. And moreover, so if we look at the residue of beta at a negative even integer, then it involves some polynomial in the conformal cross ratio up to some finite order. Okay, so this is just saying, repeating, written what I said on the previous slide. So that is just to say that if we were to, by some other means, obtain the 4-point conformal or celestial amplitude, and we wanted to extract now the effective field theory coefficients, well, all we need to do is we need to look at the residues of poles in this parameter beta, and then we can extract, in particular, so we can extract the A, K for a particular Q by taking some number of derivatives in Z and setting Z equals to 0. And so another way of saying this is that a celestial amplitude that is consistent with unitarity and causality is required to admit simple poles in beta at negative even integers with residues that obey all the positivity constraints that are specified by the EF teacher. And so just to demonstrate explicitly this fact that the coefficients in effective field theory expansion are, in fact, the residues of poles of a celestial amplitude, let's consider this very simple example. So here,
Monica,
yes.
Can I just ask about the logic in here? So the causality constraints are defined for a theory with a mass gap. And then now you seem to be applying it to sort of theory with massless exchanges as well.
My understanding was that the causality constraints don't necessarily, require, I mean, it depends on what you want to assume, but so long as you assume.
You just expanded, you did the EFT expansion as a polynomial in SNT.
Oh, you're saying it's missing, like, for example, T-channel poles.
It's missing logs if you're.
Logs.
Yes.
Yeah. Okay, actually, I have a slide on that later. So, right, good. Actually, well, I can say that
So
now.
what kind of theory are we working on now?
So for now, I was assuming that we were ignoring the running that comes from massless loops. But it turns out, and I'll say that at the end, well, it turns out that if instead you wanted to include, so this that discussion ignores running of couplings from massless particles. More generally, if you have massless particles and you have you include their loops, then you expect, right, that your effective field theory expansion takes the form something more like this. And here, basically, it's a simple property of Mellin transforms. Powers, the logarithms that arise from massless loops give rise to just higher order poles. And so you can still extract the coefficients, the effective field theory coefficients from the effective field theory coefficients of logarithms simply by looking at higher order poles in celestial amplitudes.
I see, but then you don't have the EFT constraints anymore, right?
Right. So you need to include, like, the generalization to those.
Okay. Maybe we can discuss it later on, but thank you.
Right. So what I was saying was that sort of another way to phrase this is that if you have a celestial amplitude that is consistent with unitarity and causality, then it must admit simple poles at negative even integer beta with the residues that obey all the positivity constraints that are specified by this EFT. Right, and so now we were going to look at a toy example just to see this correspondence between, or this equivalence between the coefficients of an effective field theory expansion and the residues of poles in a celestial amplitude. So here we consider just the S-channel contribution to the scattering of massless scalars that's mediated by some massive exchange. And one can simply calculate the celestial amplitude by contour argument, and this is the answer. So now, so again, this was the momentum space, scattering amplitude, and the corresponding celestial amplitude. So again, if we do the effective field theory expansion for this object, we expand in omega over m. And this is the result. And so here we can see that the expansion coefficient is minus lambda. The expansion coefficient for, let's say, for omega to the 2n is minus lambda divided by m to the 2n. And so that is to say that we should be able to take this celestial amplitude, look at the residue of the simple pole at beta equals minus 2n, and exactly find this coefficient. And again, and we do. So it is, as we would have hoped, minus lambda divided by m to the 2n. Okay, so what have we learned so far? As I said, the ectohedron encodes constraints from unitarity and causality, and an infinite number of positivity constraints that must be satisfied by these EFT expansion coefficients, A, K, Q. And in a celestial amplitude, these coefficients arise as residues of simple poles at negative even integer beta in celestial amplitudes. Now, in theories of quantum gravity, then the celestial amplitudes must also reflect the universal soft behavior at high energy fixed angle scattering that is associated with the physics of black hole production. So that is to say, in momentum space, if you look at the scattering amplitude and in the limit where you take s to infinity and hold the ratio of s over t, or in other words, the angle fixed, one expects in the theory of quantum gravity that the scattering amplitude admits exponentially damped behavior in energy. And so to see what the signature of this is for celestial amplitudes, here we sort of apply similar logic as we did to look at the effective field theory expansion. And that is, we need only consider the contribution from the upper range of integration in this formula here. And so in other words, we know that as omega goes to infinity, that the upper range of the integration, this scattering amplitude should be exponentially damped in energy. And so what we've learned is that this exponential softness in momentum space ensures, in fact, that the integral converges in the upper limit. And in terms of the analytic behavior of the celestial amplitude, what this means is that the celestial amplitude is analytic in beta along the positive real axis. And this is in fact so different than the type of behavior we would expect from a typical field theory. And so there, a typical field theory, we would expect the scattering amplitude to instead have power law fall off at high energies, and that gives rise to instead simple poles along in beta along the positive real axis. So this is just to be clear. So the poles, any celestial amplitude should have poles in this parameter beta along the negative real axis associated to the effective field theory expansion. And in a field theory, one would expect poles along the positive real axis associated to power law fall off of the field theory in momentum space, and that in a theory of quantum gravity, that all of these poles should be erased, and it should just be an analytic function of beta along the positive real axis. Okay. So let me just now provide a summary of sort of all of the constraints that I presented. And so the first thing was we used kinematics, and we found that the scattering of particles, which transform like primary operators in a conformal field theory, can be written in this form where there is this part that sort of essentially takes care of all the kinematic constraints, and all the dynamical content is now encoded in this function m, which is simply related to the dynamical content of momentum space by a single Mellin transform. And moreover, the conformal cross ratio can be identified with the ratio of Mandelstam invariance, or in other words, the scattering angle. Now, from unitarity and causality, we want this celestial amplitude m to emit an infinite series of poles at negative even integer beta, whose residues are subject to all of the EF dihedron positivity constraints. And finally, the exponentially soft behavior at high energy fixed angle tells us that m should be analytic in beta along the positive real axis. And so sort of some directions of potential interest would be that if we were to be able to obtain a more complete understanding of the analytic structure of the celestial amplitudes in beta, then we would be able to determine the constraints, the further constraints on these EFT expansion coefficients that arise from the soft behavior and momentum space at high energy and fixed angle. And another thing that I think would be very interesting would be to understand a more sort of intrinsic to celestial amplitudes derivation of the EF dihedron positivity constraints. So yes, I think that's it. Any questions?
Thank you, Monica. Let's thank Monica for this very nice talk. Are there any questions? I have a question. So I didn't get that, but the CFT, the two-dimensional CFT, is it a unitary theory, or there's nothing about unitarity which you can say?
There's no reason a priori why it need be, because it's not like ADS where unitarity in this CFT would be something completely different.
And also, is there something special about this? So if you assume unitarity on the two-dimensional side, does it give you something interesting for the 4D side?
That has not been particularly explored, and it's in part because one of the first results in this was that if you wanted to cover the plane waves, then a basis which covered the plane, people constructed essentially highest weight representations that cover the plane waves, and if you do that, you find that the conformal dimensions need to be complex. So then the thought was it's not unitary. But there's been like mostly in the past couple months, some advance that maybe one can get away from that. And actually, if you look at the way that in fact translations and some of the other more exotic asymptotic symmetries act, they move you off of the complex dimensions that you thought were associated or covered the plane waves, although you can re-expand them back on the plane waves. So anyway, the story is ongoing and it's not completely clear, but it's a good question.
Can you learn something more about the 4D from the properties of this 2D CFT? I mean, there's a crossing symmetry on top, right? There's if it was unitary, there would be some additional constraints, but already from the crossing symmetry, is crossing symmetry in 2D the same as crossing in 4D, or are there completely independent statements?
Yeah, not a lot. is known, and I'm not entirely sure.
I'm not sure if these are interesting questions, but what I would do, I mean, you could take some known to DCFT on top, right, and then just do the inverse spelling and see what happens in the downstairs, really.
Well, the problem with just taking any CFT is that most CFTs won't look like scattering in 4 dimensions, and that they won't contain the symmetry of translation and variance. So, right.
Like one of the most amazing things about this CFT is, as Monica was stressing, the 4-point function vanishes unless the 4 points lie in a circle, lie in a great circle on this on the sphere. So this is not some garden variety CFT. That's the consequence of this delta of z minus z bar, which is translational invariance ultimately.
And another way of saying that is the symmetry group is bigger. So even if you you can't have a finite number of conformal families. You have a symmetry group that now because the symmetry group is bigger, that interrelates different conformal families, and translation invariance tells you that you need an infinite number of them.
Mm-hmm.
So yeah, it's like.
Okay, thanks. Yes. Any more questions? If not, then I have one more, but if there are some other people want to ask questions, then that's good time.
Monica.
Yes.
Great talk. I wanted to ask if we understand how would these poles and these extra massive states flowing in the amplitude would appear through the in the celestial OPE in some sense? Would they appear as other operators with other OPE coefficients? Are there collinear limits involved in which these massive states are produced?
Here's the deal with massive operators. Actually, so I said, okay, one of the beautiful things about ADS CFT is that you have a quantum field theory on the boundary. Here, right, one of the sort of basic things you want to check, right, is that I told you, so maybe the first thing for everybody else is that there is a way to put massive states also in basis where they transform into a Lorentz group like primary operators in a conformal field theory. So they're associated with a point on the plane.
Right.
And there's the question of, are they like local operators, in the sense that if you move on that point on the plane close to another point, the point associated to another state or operator on the plane, do they have singularities? Do they really sort of behave like local operators? Now, for massless particles, where you do this construction that I just said, essentially because the points on the plane are still directly related to the points in momentum space, angles in momentum space, you do see this singular structure. But for massive particles, there is no canonical point on the plane associated to a massive momentum. And this is essentially because, massive momentum can be in the rest frame. So there's obviously sort of no direction associated to it. And so whether the massive particles really behave like local operators, I mean, I think in most respects, they actually kind of don't.
It's there is this conformal block expansion paper, right, that Strominger and friends put out recently, in which they analyzed the scattering of 4 scalars, but the exchange is mediated by a massive scalar. And I think the hope there is that.
Right, you can take that object, right, and expand it in conformal partial waves, and then try and write it as a conformal block expansion, which is what they did, right? But I'm saying, I guess it depends on, yes, I think that it depends on what you want out of your OPE. If you want, for example, if you wanted to take a massless and a massive particle, it's not obvious to me that they're going to have a local OP, and I kind of think they don't.
I see.
But this is not to say, actually, there's been a lot of, So I think ultimately, I think the question is, then can you use conformal symmetry and what you know about representations in a clever way to sort of get around the fact that maybe you don't have local operators? And that seems like perhaps possible. So like, I guess sort of the newest thing is that we understand that there's sort of many different infinite dimensional symmetries that underlie these celestial amplitudes. Let's say like the most well-studied being those associated with the sort of leading universal soft theorems.
Right.
But there are ways in which you can understand, any sort of sub-leading orders in terms of some sort of symmetry algebra. And, recently Andy identified them with the W1 plus infinity symmetry algebra. And so it's just, I think that the answer is it's ongoing. I'm a little, I think the locality questions, whether at least what's been worked out so far, is not super clear. And that OPE story seems to work specifically for the massless particles, which you construct in this way, and whether it works. Yeah.
They do consider higher derivative operators or some such thing in the paper, in the old celestial operator products paper, but I don't think they consider any massive couplings to the Yang-Mills fields. They just consider some.
Actually, that analysis in that paper is actually really just for minimal couplings.
Yeah. I was asking because I still don't understand if the parameter beta, or the sum of conformal dimensions of all four particles, is anything natural from the CFT point of view. Is it a natural operation to take a residue in beta in any CFT? Why would this? Okay, this is probably a very vague question, so I'm just throwing it out. But is there some kind of a natural reason why these things are organizing themselves as residues in at poles in beta? Could beta be something like a natural object in the CFT itself? Because
I think.
Yeah.
Well, I was gonna say you should ask like the CFT experts.
Yeah, it does smell like one of these Mellin amplitude things where it's very natural to have to sort of inverse Mellin transform your or Mellin transform your CFT correlator in the conformal cross ratios. So like a further Mellin transform on top of what you would have done, what we would have done. And then there are extra dimensions, and the poles in the dimensions sort of give you the operators that are flowing in the OPE, the locations of the operators that are flowing in the OPE. So you get gamma functions of sums of dimensions minus some pole location. And then you get infinite number of poles in the Mellin amplitude. And then at each of the residues of those poles, the amplitude factorizes, but then there's some residue, which you could probably think of as the OP coefficient at the associated to the operator at whose dimension you took a residue. But even there, okay, it's not the sum of all deltas. It's usually like a sum of a bunch of deltas associated to a propagator, like delta 1 plus delta 2 on one side, factorizing in the S channel. But it smells very much like that. Have you looked at these Mellin amplitudes before? Maybe you thought about this.
Referring to, but no, I haven't like.
Fair enough. That's just vague. Yeah, I can discuss later. But yeah, thanks.